complete the setting. So it's not a. Oh, this is right. Hi. So we haven't started yet. So it's still setting the computer. So I actually just upload all your homework assignment and the quiz. Well, basically the whole class is doing very well for all the problems. The only issue from what I observed for the I guess for the quiz, for the second quiz, it's like most of you are get a little bit confused about the what's the trip rate. So probably before I start the lecture today, I'll just give you the quick review about the two methods we apply to estimate the trip rate. So it's only about the confusion that you had for the for these two methods. So let me go to chapter 1. So you see that we are usually providing with you about the household, number of the household, and the total number of the trips in each cell. And the first method, the cross-classification method, is pretty simple. The rate is just the total number of the trip. Total number of the trip divided by the number of the household, which will tell you what's the average number of the trips that each household will take every year, and every day. So you need to pay a little bit of attention about what we defined, which table is for the trip table, which table is for the household. And once you know these two matrices, it will be easy for you to get this cross-classification method. The next one about the multiple classification methods. It's a little bit complicated, but basically you need to do the same thing. You need to calculate the mean trip rate, which would be the ratio between the trip rate and the total number of the household in each category, the household size or the number of the cars. So that's the common mistake that the whole class is making for the last quiz. But I believe it's just because of misunderstanding about the definitions of the cell. So it could be easily solved. So just pay attention about definition and the formulas we're going to use for the trip rate calculation. So that's the quiz. Just feel free to let me know if you have any questions about the all the examples or the homework questions. And for the third homework, which I uploaded on Area to Learn, it will give you some practice about how to use the MCA, CCA method to calculate the trip rate, as well as the using the linear regression method, which will be covered in the lecture today. Questions? Oh yeah, I haven't go to the presentation mode. Yeah. So today, yeah. I have already shared the meeting. Is anyone gonna see it? It's the link is on Family to Learn. No, it's not. It's in our Teams. So I see Xiaoyan and Haoyat there. So I guess you might be able to access to that. Can anyone open the Teams and see what kind of screen is showing now? Because on my computer, yeah, just probably mute yourself. Yeah, my computer is just show two, I guess, two displays, right? Let me see how to change the display setting. But you will not see this one here. Let's see. Anyone has idea about how to solve it to make it better? No? Maybe just duplicate show. Oh yeah. Yeah. That's better. So for the lecture today, we're gonna go to introduce the method, the linear regression method, to do the tree generation. And basically for this lecture, we're gonna cover two parts. One is about the some review about the linear regression. And I believe you have already taken some class about that. So for some of the derivations, I will go through them quickly. And then we're gonna go to check how this method is applied for the tree generation models. First, for the review, we will actually start from the definitions of the matrix and the array. And you know that for the tree generation model, in the previous two methods, the CCA and the MCA method, we only consider two different variables and how to put them into different categories. But in reality, there will be more than two factors will determine the trip rate. In that sense, the simple method, CCA, MCA method, will not be sufficient. What we do is that we will try to pursue the linear regression. This is a very classical statistical model to find out the relationship between the trip rate and the most relevant variables. And that one will rely on, for linear regression, the best way for us to analyze it is using the matrix and arrays. So first, we're going to check some definitions we're going to use for the linear regression. And here, we're going to use the variable z. Let me close this. So we are using the variable zij to represent the element, the ith element of the jth variable. So we will consider, finally, we'll consider p different variables in the tree generation model, and we will have little n observations. Those would be the variables for us to calibrate the linear regression model. So with that, you will have the n by z matrix. That will be all the observations that we have for the variables. Those would be the independent variable we're going to use. And for each observation, which would be the ith observation, you will have p plus 1 variables values, which will represent the value of the p plus 1 of the p variables, not p plus 1. And also you can find out the observations in the for each variable. And if you want to simplify the format, you can actually write them into the array. And the ZI here, ZI tilde here, will represent the observations for the ZJ here will represent the observation of the J's variable. And with that, for each variable, we have n observations. Then you can find out the mean value, which will be the average of all the n variables, n observations. And also we have definitions of the variance. And this definition, with the variance, we can find out what's the definitions of the standard deviation. Those are all the common definitions we're going to have. We can also define the covariance, which will show how the two different variables are related with each other. The correlation to determine what's the relationship of two variables. If it's close to 1, means that they're linear related. If it's close to 0, means that they are not related to each other, independent of each other. That's the vectors we're going to use to try to write down all the observations. And we're going to use the vector and arrays to do the calculation. We can also write down the covariance matrix, which will show the covariance of the any two variables. We have p variables, so here we can find out the p by p covariance. This is a kind of the symmetrical matrix with the dimension of p by p. And for any value, say that Sjk will represent the covariance of the variable j and the variable k, and Skj will be the same to Sjk. For the diagonal, that will be the variance of each variable. So this will just be the definitions of the covariance and how we can write down the covariance matrix. It's just some fundamental definitions, so I'll go through them very quickly. You can also find out the definitions of the correlation matrix for these p variables. For the diagonal, it's always 1, means that they will be the same variable. You can see the definitions of the correlation for each cell in this matrix. So regarding to the linear regression, we want to use the observed variable, which would be the z. That will be the one we can observe to estimate some dependent variable. That would be j. To do this one, we need to define the relationship or define the function, which would be function f here. The f will be the function of the observed variable z and some coefficients. But I know that in reality we have a lot of randomness. So this kind of relationship from the statistical model, we cannot describe the accurate relationship. What we can do is find out the certain probabilities, and these kind of things will include some error terms, and that will be the epsilon here. This is the problem, the general estimation problem. So in this equation, y is the dependent variable, which would be the one we want to estimate. Z is the independent variable that we're going to observe, and beta is the coefficients, which would be the coefficients we want to calibrate. We're going to use some samples to calibrate the coefficients of the entire population. And epsilon would be some disturbance, and it will follow some specific distributions. That for the function f, we know the format, and here we want to start with the linear regression. So f will represent the linear function, and the beta would be something we don't know. This would be something we have no idea about what's the values. It could be well, this thing is the one we have to determine from the sample. But this one determined from sample is only applied to estimate what's the value in the population. And the third one, for the disturbance, we have some assumed distribution of the disturbance. Usually we assume that it follows the random standard normal distribution with the not a standard normalization. It's a normal distribution with the mean of 0. So that's the assumption we made. And we're going to use all the observed data, z values, and observed dependent variables to estimate the value. What's the value of beta? And that's what we do for the for this kind of linear regression or the statistical estimation. So if we go to check the program to check the original equation, as we know that epsilon is a random variable, so you must see that y is also a random variable. If we consider this one is from the pick up randomly from the population, and the z is now a set of the vector with the known variables, and that will be something we can observe. And we want to use the z value and calibrate the beta value to estimate what's the value of y in the population. For this specific problem, say that you are provided with the populations, the income level, number of the cars, you will be able to estimate how many of the trips you're going to generate every day. So that's the basic idea about the statistical estimation. And now, for the implementations of this one, we will usually we're going to use this model to study in the population. Say that if we want to do some study in Hamilton area, we want to see estimate how many of the trips will be generated by each household in Hamilton. But Hamilton has, like the population is more than 500,000. There are so many people living in Hamilton, so it's impossible for us to know the data for every household. What we can do is in a small sample, like 1,000 households, and we can then do a survey for these 1,000 samples, which would be the any samples we can select it from the population. We know the independent variable, the household information, the household structures, the income levels, the number of the cars they own. We also can use the survey to find out how many trips we're going to take every day. That will be the value of y, which would be the dependent variable we want to estimate. So those will be the observed value. And then we're going to use this sample to estimate what's the parameters of the population, which would be the beta in the equations, in the formula we described. So generally, we can say that beta would be a function of this variable or the data we observed in the sample. So that would be the z1, y1, z2, y2, and the zn, yn. So it must be a function of those observed values. But this is just an estimation from the sample. It might be quite close to the population parameter, but not exactly the same. Might have some bias depending on the method you're going to select. So we should say that beta hat is just an estimation of the true value beta in the population, but we should also be aware about the potential difference between these two values. If we consider that g in the linear regression, then usually this function, the g function, is the least square operator. We want to find out the minimum errors between the observed trip rate and the estimated trip rate. And the other statement we have is like a z beta hat is just an estimate of the true value. So that's the two factors we have to remember for the statistical estimation. For the multivariate linear regression, there will be some properties we have to know. First of all, we can write down all the functions into the linear format. So previously, y equal to f, which is a function of z and beta. and that's the general formula. And what we can do is that we can try to get a linear format. That will be z times beta. Beta is in the vector, and z is the matrix that we observed. Here also we have the random term, and we know that we assume that the expected value of the random term is 0, and the covariance of the random term is epsilon times I. So it means that for each observation, the random term is independent to the other observations. So if we go to check the covariance matrix, we only have the values of the diagonal, and for all the other elements, like if for different observations, the covariance will be 0. And also, we know that the covariance will be, all the variance of each random term will be the same for all the n observations. So that's the assumptions we made for the linear regression. If we have to make sure that these two conditions are satisfied before we use or do any calibrations about the regression. And give you the ideas about what the covariance matrix looks like. Now we can then write them into the matrix format. Y is the observation, which will be the number of the trips we observed for each household, with n households in the sample, and Z is the independent variable we collect for each household, and then beta is the parameter, so we want to calibrate, we want to estimate from the sample. Also, we have the n random terms. So if this one will actually represent the linear format, the linear equations between the independent variable and the number of trips. Say that number of trips is linear functions of the number of the person in the household, the income level, the number of the cars, or the potential employment status in the household. Then you can define that Y would be the trip rate, number of the trips, and the Z1 would be the number of the person, Z2 would be income, and Zj would be the number of the cars, and Zp would be the employment status, and so on. So those would be the observations. And if we have the other type of the formula, different from which would be the higher level of higher order equations, the Ti equal to the number of the person to the power of beta 1, times income to the power of beta 2, and then they get the employment level to the power of beta p. We can actually apply log transformation for this equation to make them be in a linear formula. So if you do the log transformation, y would be the log t, and the z1 would be the log number of the person, z2 would be the log of the income, and so on. So for any functions which can be converted to the linear format, you can actually apply the linear regression. Yeah. You usually we need to add in a constant term for the as beta 0. Yeah, you can add it. This is just one example. You can assume that at a certain column there's no constant term. We're gonna for the examples that I'm gonna introduce for this lecture, they will have some actual settings of the equation. But you also need to be very careful about that. If we determine based on the equations that I have, sometimes you may not need the constant terms. Like if there's no person, no income, no car, definitely no trips, right? So that's the some examples, and then you can see that we can use this matrix format to find out the estimation of the number of trips for the i's households. So yi is the function of the zi and the beta, and also the random terms, the ith random terms. In this, if we write them into the linear equation, now the beta 1 times zi1 plus beta 2 times zi2, and we'll get the beta p times zip plus the epsilon I. And for the least square estimator, what we're going to do is that we will try to find out the minimum values, find out the optimal values of the beta to minimize the square root error, the square error of the observed tube rate and estimated tube rate. So here, z times beta hat is the estimated tube rate. And y minus z times beta hat will just show what's the difference between the true value, true observed tube rate, and the estimated rate. We can also write them into the S beta hat as the simplification. Another thing you have to know that for the y here, it's not the same to z times beta hat, unless you have a perfect model. But usually we won't have this one. The differences can be represented as the epsilon, which would be the random term. That's also the reason we want to introduce the random term constraint model, but will never be perfect to represent the real world conditions. And we also define the beta y hat to show what's the estimated tube rate. This is just a symbol so that in the future it's easy for us to do analysis. So yi hat will be the beta 1 hat times zi1, and you get to beta p hat times dip, which will show the estimated value of the ith observation. And you can also see the difference between the observed one and the actual one. Basically, for the observed one, you have the true parameters, beta 1, beta 2 to beta p, and the random term. But for the estimated one, we have beta 1 hat, beta 2 hat. Those would be the parameters calibrated from the sample. They are not exactly the same to the true value. Also, for the estimated tube rate, we do not have any random term. So that's the some difference we have to pay attention. And we also define a new term, which is epsilon hat. That one is defined as the residual from the regression model, which will be the difference between the observed value and the estimated tube rate. So with that, the least square estimator would just be the minimum value of the residual, the products of the two residuals, or just the residuals, to be the square of the determinants of the residual. And now let's see how we're gonna use this least square estimator to find out the estimator, find out the equations to calculate the beta values. So we define that the S beta hat will be the equation here, y minus z times beta hat times the y minus z beta hat. And we can write them if we discretize, apply the values, apply the matrix and vectors in this equation. We can expand them to this formula. We need to check whether this is the actual case, whether this matrix is indeed can be expanded here. So in these slides, I give you the detailed derivation about how can you jump from this step to this step, but I will not go through them in the class. So you can just go and check how they're going to be expanded from the matrix format to vector format, and then do the calculation. You can find out, you can get the expanded formula for the S beta hat. And the next thing we have to consider is like, you know the formula for S beta hat, And for this minimization problem, we need to know how to find out the optimal value of beta to minimize the errors. And obviously, you can try to check the first order derivative for the beta for the estimator. And at the value of 0, you can find out the optimal value of beta. So we just need to try to find out the formula of this one and find out what's the value of how we're going to solve them for the p different equations. So for the i's variable, for the i's parameter beta I, do the first order derivation. You know the formulas of s beta hat. You can do the first order derivation. And let's go to see what this is just a way to show you the details about how to do the first order derivation. And actually cancel a lot of unrelated parameters. The formula will be very simple. Basically, you can get that the first order derivative to beta I, it can just be simplified as this equation. Yj minus the expected value of the y of the jth variable, the jth observation comes zji, and summarize for all the n observations. So this is only applied for the ji's variable. You can apply this one for all the other p minus 1 variables. Put all of them together, you can actually write them into the matrix format, which can be simplified as this one. But we also need to double check whether this one is right, whether this one can be derived from this equation. They are not intuitively look like with each other. So I give you some details about how to find out this derivation. Again, I will not go through the details about the derivations. So if you go to check everything, you can find out the formulas for the first component of this equation. Exactly the z prime times y. So it means that the first part is right, and you can also go to the second part, z prime times z times beta hat, and it shows the details about how to do the derivation. Again, I will not go through the details. It's very complicated for the general situation. Basically, if we go through the whole slides, find that they are equivalent with each other. So we can say that this first order derivation for the p variables can be simplified into the matrix format, and then the solution, optimal solution of beta hat will be straightforward. You can quickly solve the beta hat as z prime times z inverse times z prime times y. So here, these are observation of all the variables, independent variables, and y is the dependent variable. That will be the truth rate. So, which means that you can use your sample data to find out, to estimate what's the parameter values. This is one of the most important equations you need to know about the calibration of the linear regression, the multivariate linear regression. It can be applied for any number of the variables, from 1 to 100 or even more. And now let's recall the definition about the estimated trip rate. Y hat will be z times beta hat. We can then find out the estimated trip rate based on the value of beta hat from the model. So I'll give you the y hat as z times z prime times z inverse times z prime times y. And we can also find out what's the residual, estimated, what's the difference between the true value and estimated true rate? And that will be y minus y hat, which we'll show in this equation. We can also go to check what happens for the z prime times epsilon hat. If we go to check the details of this calculation, you will find that z prime times epsilon hat will just be 0. So that's several equations we have for the multivariate linear regression, and we're going to use these equations to determine the properties of the linear regression model. So another thing we want to consider is the transpose of the estimated value. The transpose of the y hat would be beta hat transpose times z hat. This is the properties of the transpose for the matrix. And if you use the if you multiply y hat transpose times the residual, you can easily get the value as beta hat transpose times z transpose times epsilon hat. And we know that the transpose times epsilon hat will be 0, so definitely this one will also be 0. So this will give you another feature: y prime y hat transpose times epsilon hat will be 0. And now we want to go to see the another features, which will be the product of y transpose and y, and we can go to see what's the value, what's the expression for this one. So for this one, we can do a little bit expansion for each component, for each vector of y. We can add the y hat and minus y hat, so it will still be y for both components. And then we know that y minus y hat is epsilon hat, which will be the residual. You can get the value as y hat plus epsilon hat transpose times y hat plus epsilon hat. And with this one, you can see that in this equation, y hat transpose times epsilon hat, which will be the one we define here, it's 0. And similarly for this one, it's also 0. So you can get a simplified result, which will tell you that the product about the y transpose and y will equal to the product of the y hat transpose times y hat plus the product of the epsilon hat transpose and the epsilon hat. So this will give you the relationship between the observed trip rate and the estimated trip rate and the residuals. So that's the first feature we estimate. And now let's see more details about what's the expected value of the parameters beta, and what's the variance, covariance, and so on. Which will give us more details about whether the model, the estimator, is unbiased or not. So we have some definitions. First of all, we have the linear formulas for the relationship. And then we have the definitions about the descriptions about the random term, mean 0. Covariance is epsilon squared times sigma squared times I. And we know that y hat equal to z times beta hat, and the beta hat equal to z transpose times z inverse times z transpose times y. So these would be the features we either assumed or obtained from the multivariate linear regression. Epsilon is the random variable, yeah, and epsilon hat is the residual between the estimated is just the y minus y hat. So they're different. Also, we have the formula equations for y hat. It's just the beta hat, just the z times beta hat, apply the beta hat value. And then we also define the epsilon hat, the residual. And we know that z prime times epsilon hat is a 0. And the y hat prime, y hat transpose times epsilon hat is also 0. And y prime y are equal to y hat prime times y hat plus epsilon hat prime times epsilon hat. This would be the equations we estimated from the previous slides. And now let's go to see if we apply the formula of the y. We know that for the true value of y, it's a linear function of beta and the actual random variable epsilon. So if we put y in this equation, you can beta hat also becomes a random variable. We can then do some expansion and simplification about beta hat by do some calculations. We can find that beta hat equal to beta plus z transpose z inverse times z transpose epsilon. So this is the expression to show the relationship between beta hat and beta. Beta hat is the estimated value. Beta is the true value from the population. Let's go to check the expectation to see whether beta hat is an unbiased estimator. If the expected value of the beta hat is the same to beta, then we can say that it's an unbiased estimator. If there are some difference, then it means that it's not. So we do the expectation for the beta hat. Also, you need to know that beta is the true value for the population, so it's a constant for that population. So expectation of beta is also beta. And also you have the for this equation you only have a random variable of epsilon. Do the expectation. Expectation of epsilon from the definite assumption is 0. So we get a expected value of beta hat is just beta. So it means that beta hat is an unbiased estimator of the true parameters in the population. So this is quite important. If it's biased, it means that your estimation is not correct. We call this one as the unbiased least square estimator. Another feature we can try to think about is trying to identify the potential of expectation. Try to check whether the expectation of the residual is 0 or not. If it's not 0, it means that your estimation is not quite accurate. So similar to the previous analysis, we represent the y with the linear equation z times beta plus epsilon, and epsilon is a random variable. And now we can go to check the expected value of the epsilon hat. First of all, we can do some simplifications, and with this simplification, we get a very simple expression. Epsilon hat is 1 minus z times z transpose z inverse z transpose times the epsilon. And then you do the expectation. Obviously, you can still find that the expected value of the epsilon hat is also 0. So it means that your estimation, the residual shows the difference between the true trip rate and the estimated trip rate. If the expected difference is 0, means that your estimated value and true value will be for the whole sample, or for the large group number of the observations, it will be the same. There's no difference. Another feature we have for the multivariate linear regression. And now let's go to see more details. Try to identify the covariance. So before before we do that, we will try to write down the matrix of Z into the vector, and this one can be written as the Z prime. Another Z prime will represent each one will represent the one variable. And then let's go to see the some more details. Say that we know we define the mean value of the Z as mu Z. It will represent the average value of each variable. So Z1 bar will represent the average value of the first variable. Z2 bar will be the average of the second variable, and so on. So that's the definitions we have. You can also find out what's the covariance matrix of the Z vector. We have this is the definitions of the covariance. The calculation again it's quite complicated, so I will just give you quickly help you to jump to the. You can find out the covariance with this table. You can find out the covariance of the J's observation and the K's observation as this equation. And then we just write them into the covariance Z. So this is the covariance of the observations for the independent variable. Another feature about the matrix operation, and especially about the matrix with respect to the covariance, is that if we have a new variable x that equals to C times Z, we know the covariance of Z is 0 with Z. Then we can calculate what's the covariance of x. For the covariance of the x, this is the definition of the covariance. And we're going to find out what's the value of the mean values for x. So as C, capital C is in a constant term, so what you can get that mu x will be just C times mu Z. So this we just take the constant matrix outside, and then you can go to check what's the covariance based on that definition. Put the formulas of x and mu x in this equation, and the covariance of x as so get the equation like this one. And another thing, you need to think of another background. There's a lot of background here, but hopefully it will be helpful for you to understand the derivations. So if you have a product of two matrices, A times B, then you can get the value, you can get the result as this matrix. Say that A is 3 by 2, B is A is 3 by 2, B is 2 by 3. So A is 2 by 3, B is 3 by 2. And now you can go to check the transpose of these products. So the A times B transpose, if you do this one, you can find that A times B transpose will equal to B transpose times A transpose. So this is always true for any two matrices which can multiply with each other. And we can then take this conclusion for our previous equation. So we have C times another matrix here, so we can change their order and apply the transpose to both matrices. With that will be the C times equation inside and times C transpose. We know that C is constant, so we can take the C out of the expectation calculation. And with that, you get covariance of X will equal to the C times the covariance of Z times C prime. So that's the relationship between the X and Z and how they're going to change the expressions of the covariance. And now this is just some background information. And we're going to use this information to calculate the covariance of the unbiased estimator. So we know the covariance of the epsilon is a sigma squared times I. And we also know the expression of the beta hat, which would be the showing the equation 3 here. We need to find out what's the covariance of the beta hat. So which would be the covariance of this equation. We can then apply the original definition of y in this equation, which will give you the well, I guess first we probably need to apply the conclusion we just made. So for this one, you can consider capital C as Z transpose times Z inverse times Z transpose. So you apply C and C prime in the front and at the back of the covariance of Y. So this will be the covariance of beta hat. We have C and C transpose. And now, if we want to find out the actual values of the covariance of beta hat, you need to know what's the value of the covariance Y. So we know Y equal to Z times beta plus epsilon. For Z and beta, they are all the constant values for the entire population. So we can then actually consider that the covariance of Y is just the covariance of epsilon. And another thing for this one is about the how to do the calculation of this transpose. You can just quickly change the order to do the calculation. And for the covariance of Y, it will be the sigma, also be the sigma squared times I. If you put this equation in this one, we can get it like covariance of beta hat sigma squared times Z transpose Z inverse times Z transpose times I times Z transpose Z inverse. And you know that for the I in this kind of product, you can actually take them out. You won't change the value. So if you go to check the details of this equation, you can cancel these two terms, and if you use the value as covariance of the beta hat, it's a sigma squared times Z transpose times Z inverse. So this is the covariance of the beta hat. And that's another equation we derived to represent the properties of the linear regression. And of course, we can go to continue exploring the properties of the other variables like the covariance of the residual. Let's go to see. For the covariance of the residual, if you do apply the similar process, do this calculation, even though you can see in a very complicated formula, but if you do the calculation, you can even a very simple. That will be the sigma squared times I minus Z times Z transpose Z inverse times Z transpose. So that's the covariance of the sigma hat for the residual. Well, if you're interested about details, you can try to do the calculation. Follow this slides, do the calculation by yourself. I help you to get familiar about what's the how to do the computations for the matrix. So we started with around like almost 13 equations. Most of them will be the properties of the linear regression. We can always go to check something more. If you, for example, you can go to check what's the covariance of the y hat, what's the covariance of expected value of the y hat and so on. But that's something we will not further explore here. Another thing we want to introduce here is some hypothesis tests about the parameters. Like for the multivariate linear regression, say that in your survey you have conducted doing a survey for 10 independent variables, and you can definitely apply all these 10 independent variables to do the regression. But one of the key part is that you have to identify whether you can remove some of the variables from your model, because some of them will have less impact to the estimation of the trip rate. And with less number of the variables, you will have less effort for you to collect the data in the future to calibrate, to do the estimation of the trip rate. So the first type of the hypothesis test for beta hat is trying to check whether one parameter is significant, variable is significant, whether we can remove it from the model. So to do the hypothesis test, we need to record all the features we have, the properties of the regression model we have derived previously. So this would be the properties we derived. And for the hypothesis test, we assume that the trip rate yi from the ith observation is in it follows a normal distribution, and the mean value is yi bar, which would be the expected value of the trip rate, and also the variance is set as sigma square. We know that the variance of the y is just the variance of the epsilon, which is what we assumed. So we have the value here as the variance here as sigma square. And we also know the definitions of the formulas to estimate the beta hat. And we have the expression, we have the covariance, of the beta hat as we derived previously. And now, with that, we can get the covariance of the beta hat. That will be sigma squared divided by C ij. And this kind of Cij will be the inverse of the Z transpose times Z. I just try to make it simplify the using another symbol to represent the values. And with that, we have the variance of the beta hat j, which would be the j's variable. The variance of this one you can find from this covariance matrix, the sigma square divided by Cjj. And we also know the expected value of the beta hat. The expected value of beta hat is just the beta. So we have expected beta j hat is beta j. And then we can claim that the beta j also follows a normal distribution. The mean value is beta j, and the variance is sigma square divided by Cjj. So that's the distributions of the beta j hat. And for the if you want to do some transformation about the beta hat, you can try to define new variable z. We got the beta j hat minus beta j divided by sigma squared divided by square root of Cjj. With that, z will follow the normal distribution. So this is the standardization for the variable. Go ahead.
Sigma square is the variance of the.
Sigma square is the variance of the random variable, the random term, epsilon, in the definition. This is the assumption we made for the linear regression model. So this is the case. You know the true values. You know the true values of the beta j. You know the true values of sigma. But in reality, you don't know what's the value of the beta. What's the value of sigma? Because that's the That's the population true values. We have no ideas about what's the value about it. As we don't know sigma, we can only use some unbiased estimator of the sigma to represent the sigma in that equation. We know that for the variance, if we go to check the expected value of the epsilon sigma hat is 0. That's what we derived previously, and which means that the is an unbiased estimator of the sigma, and if we want to calculate the variance, which will be sigma square, we can use the epsilon hat to do the calculation, and that's what we can find here, which will be the epsilon prime hat times the epsilon hat divided by n minus p minus 1. So the here p is the number of the variables, independent variables in the model. Also, you have to be aware about the definition of the epsilon hat. And so here we can then use the capital S square to represent the sigma square. So this is an estimator for the variance. It's not the true value, but that's what we can get from the sample. With that, if you replace sigma square with the S square, then the normal distribution of this one is originally the standard normal distribution will become a student T distribution with the degree of freedom as n minus p minus 1. So the normal distribution and standard T distribution are quite similar to each other, but not exactly the same. Usually the normal distribution is relatively smoother compared with the student T distribution. So so with that, we can then further simplify the value we want to check. So here we replace S, define new variable S beta j equal to S naught divided by the square root of Cjj, and this one still follows the student T distribution with the degree of freedom n minus p minus 1. Now for the hypothesis test, we want to check whether the variable j is significant or not, which means that whether beta j should be 0. If it's 0, it means that we don't need to use the variable j in the model. So to do the hypothesis test, we have a null hypothesis. We assume that the beta j is 0, so that's the null hypothesis. And then we're gonna under the null hypothesis, the beta j is 0. Then we will have the statistics p equal to beta j hat divided by S beta j. Now you can go to check the standard T distribution. This is not standard. This is student T distribution. You can see the distribution is quite similar to the normal distribution, but not quite smooth at the peak around the peak of the around the 0 values. And we can then find out the value of the statistics, which will be the beta j hat divided by S beta j. Say that it's around someplace here, and then the two regions. The yellow region shows the probability smaller than the statistics, and the blue region shows the probability higher than the statistics. So we want to make sure that the probability of this blue region is small enough so that we can reject the null hypothesis. So with that, we want to calculate what's the probability of the blue region. Basically, if the blue region divided by the yellow and then the blue region, just the blue region. Because this is the probability. So basically, if we do this one, and usually we will use some for this kind of hypothesis test, you're going to try to find out some statistics with the R or MATLAB code to do the linear regression. It will tell you the significance, and based on the significance level you define, say that 5%, if you find that significance is less than 5%, it means that the parameter is significant and it cannot remove from your model. But if it's smaller than that, it means that we cannot reject the null hypothesis, and probably the parameter is not significant. So that's the part about the hypothesis test. And another variable we need to think about is the R square. This one will tell you how good your model is. It's basically kind of the measurement about the goodness of the fit to your model. So here I'm going to just show you some how we're going to define the R square for the multivariate linear regression. We can get a definition from the equation 6 we derived previously. Z prime times the epsilon hat equal to 0. We know the definitions of the Z. Here, we assume that the first column is 1, means that it's the constant value. Then, for the first element, if you, as Z prime times epsilon hat is 0, so if you do the summation about epsilon 1 hat, epsilon 2 hat, here go to the epsilon n hat, they should be 0. And this indicates, we know that epsilon I hat equals to yi minus yi hat. So the summation means that summation of yi minus yi hat is 0. So if we summarize all the observed value and summarize all the estimated value, they should equal. The difference should be equal to 0, which means they should be the same. And it means that the mean value of the observation and the mean value of the estimation will also be the same. And we also have another equation that we derived previously. It shows that y prime y equal to y hat prime times y hat plus epsilon hat prime times epsilon hat. So this is the equation for us to define the R square. And let's go to see the details. You can actually apply two a same term minus the same term on both sides of the equation. So that's the m minus y bar square. As we know that y bar is the same to y hat bar. So this means that we can replace y bar here as y hat bar square. Then for this one, you can actually get a simplification. Basically y prime y minus m y bar square will equal to the summation of yi minus y bar square. And similarly, you can find out the equation on the right side for the estimated Q rate. So in this case, you will have three terms. This is from the observation, this is from the estimation, and this is the error terms. And we define this term as the total sum of the square deviation from the deviation from the mean or from the average value of the true observation. And this one will represent the regression sum of the square deviation, which will be the part can be explained by the model. Part would be the residual sum of the square deviation, this is the part that we cannot be explained by the model. Then, based on that, R square is defined as the division of the part can be explained by the model divided by the total sum of the square deviation. As this part is always non-negative, so this value should always be smaller than 1. And if it's close to 1, it means that the model can explain more to the data. So that's the that's what we can define. Or it equals to 1 minus the summation of the epsilon squared divided by the total value. And if you go to check more details, the more detailed definition, R squared equals the variance in Y captured by the model divided by the total variance of Y. So which would be the part explained by the model to the total deviation. So that's the R square, and another thing that I want to include is try to get more features about the models, different models with different parameters. Like we can compare the model with one parameter with respect to 5 parameters to see which one is better. And so that one will rely on the F test. So this is actually an improvement, another method to check whether what's the best model for you to use for the data you collect. For the previous hypothesis test, you can only check whether one variable is significant or not. But with this one, you can check multiple variables simultaneously, or even you can check all the variables. So that's the advantages of the F test. We're going to use the F test to compare the complete model and the totally restricted model. So here we're going to still recall the features we derived previously. That's the definitions, assumptions of the linear regression model. We have the method verification to estimate the observed traffic, observed future rate, and estimation of the parameter coefficients. And now for the unrestricted model, it means that we're going to the unrestricted model in here, it indicates that we're going to use all the P variables. So we have P observed variables, number of the person, number of the cars, the employment status, and so on. Use all the variables. We put all the variables in the model, and then we define this model as the unrestricted model. And now we can then replace beta hat with the beta hat U to represent the result we calibrated from the unrestricted model, and the y hat U represent the estimation from the estimated trip from the unrestricted model. So that's the new definition, and we can find out the sum of the squares for the unrestricted model. That will be the sum of the square error for the yi hat and the yi. And this is what we conclude for the unrestricted model. And another thing that we can do is about the restricted model, which means that we're going to take some variables out of the model, or even take all the variables out of the model. So here, let's consider the case like we remove. We just remove. Start with the case we only remove one variable. Say that the variable p. Variable p is not considered in the model. It means that we just set a variable p, the beta p as 0. With this situation for the restricted model, we don't need to think about the last column. just use the all the rest the p minus 1 variables to do the regression, and with that we can find out the sum of the square for the restricted model. We define this one as the QR to represent the restricted model. And now we will have the sum of the square for the unrestricted model and the restricted model. Usually for the restricted model, the value would be larger than the unrestricted model. That's because the for any situations, even for the one variable that is not significant, the add more variables, you can make the error smaller. And that will give you the case that QR is higher than QU. With that, we can find out the statistic. So which is the F star. That is the QR minus QU divided by the number of the restrictions, which means that how many variables you remove from the model. And divided by QU divided by n minus p. QU is the value from the unrestricted model, and n is the observations, p is the number of the variables. So this statistic follows an F distribution. This is the general density functions for the F distribution. You're going to use this statistic to check whether the probability is smaller than the part that is higher than the F star is smaller than 5%. If it's higher, we can reject the assumption like the restricted model and the unrestricted model are the same. So this is the F test. It will tell you whether you can use the restricted model. If this probability is higher than 5%, we can use it. If it's not, then we cannot use it. So this is the case for adding one variable. But as I just stated previously, the F test can help us to check which one is better, or whether we can remove more than one parameter variables in the model. So with that, I will give you consideration an example about the extreme case. The case about the totally restricted model, which means that except the constant term, we remove all the variables to see whether it's necessary for us to, whether it's possible for us to just use the average value to do the estimation. So so this is the unrestricted model. We have all the values. We have all the estimated trip rates. We got the calibrated parameters. And for the restricted model, we only have the beta 1 as the value. For all the other betas, it's set at 0. So this is a totally restricted model. With that, we have, if we recall the definitions of y hat equal to z times beta hat, you will only get this equation. So all these parts will become 0. Apparently, if we do this analysis, you can find that for the totally restricted model, beta 1 hat will just be the mean value of the y hat. So it's just the average of the observations. And then you can find out what's the difference to the summation of the sigma I hat is also 0. And I will just skip this part. Find out the sum of the square for the restricted model, and which, if you go to check the values y hat r for the totally restricted model, it's just the y bar. And if we go to check the definition of the variance, this one will just give you the value of n times sigma y squared. And you can then compare this one with the R-restricted model and then conduct the F test. For the F test, in the statistics, the number of the restrictions will be all the other variables. So we actually have p minus 1 variables removed. So this one will be p minus 1. We have the n of iterations and p total p variables. You're going to check what's the F statistics and then use the F distribution to double check whether you can use the totally restricted model. If it's a probability is higher than 5%, it means that we cannot reject that assumption. If it's smaller than 5%, then it means that we cannot use the totally restricted model. So, that's what I guess I'm gonna stop here for a while. Let's take a break for 10 minutes, and I'm gonna show you the examples about the linear regression model. Okay, just take a break.
Question about the assignment?
Yes. Let me just adjust my mask. Yeah.
So Professor, then there is equation y equals beta naught plus beta 1 z1. This is first one. Second is y equals beta naught z1 beta 1, something like this, right? So when you transform this ln y,
Yes.
and then ln of beta naught plus beta 1 ln 0, right? Then this will give me this y, then I will assume this r, and then I will do the matrices, and I will get value of r. And then I will transform this to e equals y equals er equals y. Then the r square that I should calculate.
Yeah, R square calculates based on the log transformation. It's not based on y. So at that time, for the regression, just to use the, no matter what kind of transformation you made, just to use the completed linear format to do all the calculations, R square and anything else.
Okay, because I converted this to this, so I get highest for I get r square 0.98 for this.
Yeah.
0.9, but this one 0.9. But this one, if I consider R, it is 0.8 or something. 8.87.
Yeah. That's possible. Yeah.
Because I was just confused because R square for this one is because strips generate like if you can calculate R square from this also and this also.
Yeah, because you have to know that you cannot use y, because the R square, the calculating R square also needs to assume that there's some residuals, right? If we use the y directly, the residual is not zero. Yeah, it means that your algebra is not right. So for the statistics model, it has a lot of rules and assumptions. We need to follow these assumptions to do all the calculations.
And the assignment we should do R square based on the norm.
Yeah, based on the norm.
Thank you.
Yeah, so that's actually what we asked them about. But that's, I'm not worried about the exit part, but I'm not sure, that's the thing. It's not, no. Yeah, I mean, just explain the concept of the problem and stuff, it's like that. So that's why, like, I think the presentation will be hard, but I don't want to have to solve it. That's the part that I'm getting. Sorry. Yeah, exactly. I mean, hopefully. Yeah, I'm not looking for it. Now I'm not. The midterm is Joseph. Yeah. That's what I'm saying. And it's about all this stuff. Which helps me. I'll try. I'm trying very well. And I check the assignment and they are told that they have usually the back end. Okay. I think right after. I don't know if it was sending it up we were getting this. That's not going to work for what we need.
So I guess that I go through this one faster than I expected. So probably can end our lecture today earlier. Before we I'm gonna finish the example, and after that I'll give you some brief introductions about the what are we gonna do for the midterm exam.
I was wondering about the next assignment. Explaining maybe the example that we were on the same class.
Someone have some call.
So what we have to do, we want to talk about the slide that no, after you can ask if you want no rush to go home.
Okay, so I'm gonna give you an example about how we're gonna use the motivated linear regression model to do the to conduct trip generation, and also link back to the example we explained previously about the demand and supply curves. So here's the example. We consider the same example that we used in the previous chapter. Considering we have the 2 towns A and B, and we have the, but here we assume that the average income in town A is 25,000, and the residents in town A would like to participate in many activities in either in town A or town B, and we connected by 2 routes, route 1 and route 2. The distance, we know the distance is 5 miles. The traffic for both routes, they will be governed by the green shield of our diagram. We have all goes through this process about the calculation of the travel time with respect to the flow rate. And this is the green shield of our diagram. We have the pictures for each one of them. In this example, we assume that for town A, the free flow speed is 70 miles per hour, and the maximum density is 175 for route 2, it's 60, and maximum density is 300. And the distance is provided at 5 miles. And for the residents in town A, they need to take about 3 minutes to complete the trip for any activity. And for town B, the travel time is determined by determined by the conditions on these 2 routes. And we also have some assumptions about the price of the activity. The price of the activity in town A is $4, and in town B $6. Now we want to estimate the demand of the trips from town A to town B, and also what's the demand inside town A. So to do that, we conducted a survey about 10,000 of the residents in town A, and they will report their number of trips to take, in town A, town B, and also they will identify what's the purpose for them to take the trip, and the average price they spend for those activity, and the average travel time of the activity, and their yearly household income, and we summarize all the results, and this will be the result. Even though we say that it's 10,000, but just as a paradigm. So number of trips, the average price for each activity, the average travel time, and the household income. So with that, we can try to apply the linear regression model to identify the relationship between the trip and the 3 other independent variables. So for the model, we see that the kind of activity will happen, it's still the same thing, will happen between 10 a.m. and 4 p.m. And we have the model, a linear regression. It's not exactly a linear model, but it has the way for us to convert them to the linear model. We say that the number of the activity, daily trip from location A to location I to location J, it's governed by this equation: A0 times Pj to the power of A1 times Dij to the power of A2 times I to the power of A3. Pj is the price of the activity at location J, and Tij is the travel time from I to J, and II is the household income at the location I. So those would be the variables we can observe, and A0 to A3 would be the parameters we want to calibrate. So that would be the model, and we can also have the surveying data. Now we're gonna apply the linear regression model to determine what's the value of A1 to A3. But first of all, we have to convert them to the linear format. So we apply log transformation on both of the relationship. So we have the log Tij equal to log A0 plus A1 times log Pj plus A2 times log Tij plus A3 times log Ii. So that's the linear equation. So what do we do now? We apply the log transformation for the original equation, which means that we also need to do some log transformation for the surveying data. So here we assume that y equals to log Tij. Z0 is just 1, and Z1 is 1 Pj, and Z2 is 1 Tij, and Zp is 1 Ii. With that, we now and then use the surveying data and identify the value of y, Z0, Z1, Z2 to Z3. So this is what we have from the raw data. And now we know that y equals log Tij to the line operations. We get the value of these 10 observations. And also for the z, we have Z0 is the constant, so it's always set as 1. We have log Pi and log Tij and log Ii. Those comes from survey data. Yeah, go ahead.
The speed variable in the question it was said that it is either $4 or $6.
The speed variable.
Yeah, Pj, price of activity.
P is the price of the activity, yes.
But in the question it was given that it is either 4.
No, it's the questions tell you the activity, the average activity in town A and town B. But this survey does not care about which town you are taking. It's just a specific for the specific trip, specific activity in town A or town B. So this probably the trip to town B with the cost of $6.3 just for that specific activity. But if you go to check average activity in town B, it's $6. Yeah. And also for the travel time, it's a consistent survey. It tries to identify the trips at different time of the day, different activities, and the household with different income levels. So with that, we have the dependent variable y, now independent variable z. Now we need to find out the value of A0 to A3, and if we can recall the equation we get, beta equal to z prime times z inverse times z prime times y. To find out what's the value of z prime. It's just doing the transpose of the z factor. This is the matrix of z. Z is a 10 by 4 matrix, and do the transpose by 10 matrix. Then you can do the calculation. Z prime times z, which would be the 4 by 4 matrix. Well, obviously you need to use some programming languages or the Excel to do the calculation. And find out the inverse of z prime times z. Then calculate what's the value of this inverse times z prime. It's another 4 by 10 matrix. And eventually you can calculate the coefficients. In this case, we have 4 coefficients. The first one is log A0. We have second one A1, A2, A3, and the value is 2.3 or 2.7. minus 0.2, minus 0.8, and 0.1. And this will give you the calibrated parameter, calibrated linear equation. So ln Tij will equal to this equation, and then we can convert it back to the original formula. It's Tij to the exponential operation on both sides. Now we 15 times Pj to the power minus, I guess there will be something wrong, minus 0.2 times Tij to the power minus 0.8 times Ii to the power minus 1. So that's the Tij. This is the model we calibrated, shows how we're going to estimate the trip from the location I to the location J. And now we have the model. We need to think about how we're going to use the model to estimate the trip from A to B. From the problem, we want to know the hourly volume on route 1 and hourly volume on route 2 between 10 and 4 p.m. This is the model we calibrated, and this one can actually apply for the trips in both A and B. So for the trip from, we actually care about the trip from A to B, because for both route 1 and route 2, it will be the trip traveling from A to town A to town B, right? So TAB will represent the total number of trips from A to B. And in this case, A will represent I, B will represent J. So A is the origin and B is the destination. So you need to apply the variety index for this equation, for this calibrated equation. So Pj in this case would be the PB, which would be the price of activity in town B. And Tij will be TAB, that will be the cost of the travel time from A to B. And II, which will be the first index, it represents the income and the origin. So now with the income in town A, for this program, the income is 25,000. Average income is 25,000. We know the value of the price. The price of the activity in town B is I guess $6, and the income at the time is $25,000. This one, it gives you the again, this is still minus 0.2. So it gives you the value of the relationship between the trip rate and the travel time. All the others will be constant for this example. With that, you can simplify this one as TAB will be 14.46 times T capital AB to the power minus 0.8. And so this is the total number of the flow. We're going to total number of the flow will travel from A to B on both route 1 and route 2. So the flow in route 1 plus the flow in route 2. And now for the supply curve, we can easily capture it from the Regression fundamental diagram, right? So we can find out the Regression fundamental diagram and determine the travel time with respect to the number of the trips every day from A to B. And then we can apply this equation. That will be the number of the trips with respect to the travel time. That will be the demand. If you put them together, draw this kind of demand curve with this equation, that will be another one. These two lines will intersect with each other, and the intersection would be the equilibrium point. So with that, you have the travel time, you have the number of the trips around the 2.9, and the travel time around the 7.3 or 7.4 minutes. So it's basically, you have this equilibrium point, you can find out what's the flow it is on in round 1 and round 2. So that's the way for you to combine this kind of linear regression model with respect to the demand and supply theory. Of course, if you are provided with the travel time from one point to another point, you can directly calculate how many flows it is from origin to destination. So that's the that's what we get about the results. And back to the original cost function. The volume on route 1 is 3,000 and the route 2 is 39,000 or 3,900. So I guess that will be all for the heavens. That will be all for the material lecture today. Do you have any questions about that? Yeah. The last slide, which that was the thing. Yeah, it's the same. It's the same example to the previous one. Okay. Yeah, just a different way to solve it. For the demand. Yes. Yes. So the previous one, it comes from the SAT equivalent. But this one we are not defining any utility functions. Instead, we do some survey about the how the person in these three houses taking the make their trip decisions. Same way, same purpose, different methods.
Okay. And in slide 49, it's when. So if I want to calculate the trips in AA,
yes,
I could use the same.
I use the same equation. The only difference is like
P, right?
P, yeah.
Okay.
So I is A, T is also A. So we need to use PA. The price of activity on A. So PA is the travel time of the activity inside town A. Yeah. And IA is the income level in town A, right? Yeah. So we have all the values. PA is $4, right?
Yeah.
TA is 3 minutes.
Yeah.
And IA is still 25,000. So if you put them together, you can determine how many trips it's generated for town A, just inside town A.
But that would be a constant, because there's no there.
There's no, because you don't need to do. You have all the information. Exactly. So you don't need to do any demand and supply. The demand supply is basically trying to give you a connection. Trying to give you a connection about the flow on the road and the travel time. But for town A, they simplify everything.
Yes.
Everything inside is constant travel time.
Yeah.
So nothing for you to do. Yeah.
Okay.
Okay. Any other question? For the homework, it will be very similar questions. I just give you more data, and you need to do the calculation by Excel or MATLAB or Python. Either way is fine. Show me the details about the calculation steps, like how you get the matrix like a z prime, z, and the inverse, and so on. So show the details.
You said not to use calculator, so to do it this way. But can I use already in the functions that I can use?
You mean using something like the regression functions directly to find out?
No. I mean like functions of nature.
Oh yeah. The same thing. Like I don't want you to calculate everything by hand, right? But I give you like I give you like 100 data, right?
Yeah, exactly. Okay, good.
Okay. Any other questions? Yeah.
Actually, Professor, on slide 21.
Slide 20. This one? Next one?
Yeah, the multivariate linear regression.
Which?
I was referring to C matrix.
31, right? 21. I'm sorry. Sorry. Just a moment.
What is it like the correlation between 1 and 1 and 2 and 2?
Oh, this is just one example to show you how you're going to find out the covariance within a constant matrix. So C11 is just a constant value. It's not related to the one we analyzed previously. It's just consider this as a constant matrix. It's give you some demonstration because we need to use this. We need to use this conclusion to like this conclusion. If it's x equal to c times z, then covariance of x equals to c times covariance of z times c prime. We have to use this conclusion for the derivation of the calculation of the covariance of beta hat. So it's the same thing, right? For the covariance of the beta hat, that would be the beta hat is something, it's a c times y, almost the same thing, same format, and you put the c in the front, c prime behind, and do the calculation. Eventually, you can find out the covariance of beta hat, and we need covariance of beta hat for the hypothesis test. That's the reason we do a lot of derivations about these features.
So the standard error will be just the square root of the diagonal elements.
The diagonal is the variance of the the covariance of the same variable, right? Only for the other elements, that will be the covariance of different variables. Okay. Other questions? No. Okay. So then I will give you some information about the midterm exam. So for the midterm exam, it will be the other Tuesday. That will be March 15th, right? March 15th, and it will be same time, and it will be 3 to 6 p.m. You don't need the 3 hours, 2 hours. So we'll be online, so you don't need to come to campus to do the exam. The exam will cover all the materials from the first lecture to this lecture, but exclude the Amazon part. Amazon is just for the simulation. So the for the exam, you don't need to. Well, in this class, I introduced a lot of theoretical derivations. You don't need to care about how to do these derivations. Just to give you some information about how all these conclusions are derived from the original assumptions, but you don't need to know the details about it for the exam. Basically, you have to know how to use the conclusions from all these lectures to complete the problem. And the questions of the midterm exam will be very similar to the we should say similar to your homework exam and some of your quizzes. The calculation will be simple, but you need to read through the questions. And one key point is that you have to write down all the details about your calculation so that I can check whether you do it at the right method. Otherwise, if you made something wrong and they don't have any details, then I cannot find out where I can give you some points about it. Right? So so that would be the midterm exam. There will be 4 or 5 questions about the exam. You can use the computer, Excel, to do the calculation. But as I say that if you use computer, you have to write down all the details in the exam sheet. And once you finish all the questions, take a photo or scan it, upload to Estimator. Yeah. So I guess that's well, you have already taken a lot of exams online, so I don't think there's any issue about it.
The next week lecture is not going.
Yeah, next week. I mean, probably for the rest of this term, I will try to maintain the lectures online. We have next week. I will introduce the trip distribution model, and once I finish the trip distribution model, I will introduce another method for you to do the OD matrix estimation, and that method will be related to the software, which is the Prince OD. Is that we need to go through the tutorials about the Prince OD, and after that we will try to learn the discrete choice model. And depending on the time left, we will work on the tutorial for translate. So that's the plan. So because we have something mixed with the software tutorials, I guess it's better for us to do everything online.
So what about the final project?
The final project will be provided to you 1 month before the final end of the final, so probably around some days after the midterm exam, March 20th around. So you have 1 month to work on the final project.
Like individual or?
Either it's individual. Yeah. Okay. Well, it will be pretty simple. And, all of them you can find out all the points in the lectures.
It's just like a little concern. So, homework 1, or sorry, homework 2. What I did was I first tried the numbers on the example, and then I used my own ones.
Yeah, that's the right way to do it. The one listing the questions. Just I just want to see how you can draw the isolated curves.
Yeah.
But regarding to the demanding curve, you need more granular curves or points. So you need, which means that you have to draw more values.
Exactly. Yeah. So like for what I saw or what I noticed is that there's like a difference in the calibration or the tuning or whatever of like because I was doing it on ARM, like the data one, and so the accuracy changed a little bit from the numbers in example to my numbers in the
It's just fine because more for all the softwares, program languages, they have their own regulations. So
Yeah.
remember, it's obviously, especially for the case like for those some specific scenario, they will be sensitive for these small changes. Unless you have very small intervals about the total utility that is specified,
Yeah.
you can get an accurate result. But otherwise, you always get some errors.
Yeah, exactly. So, I mean, what I would like to ask you, so because what I was thinking is if something like this comes up with filter, since you have a restricted
That'll be fine. What I do, you probably can see that on the meeting, on the homework. What I do is check in the process
Okay.
and some approximate values.
Okay.
I understand there will be errors. So unless if you are not having a very huge errors, that'll be fine.
Yeah, okay, because I even thought of maybe getting the isolated curve programming, but then drawing the functions manually, because honestly, it's so much easier.
Yes. If you draw it manually, you probably need to make sure that the scale is correct.
Yeah. Yeah.
But
Would
it's
that be okay?
It's fine. Yeah.
Okay.
Or if you can, I mean, for the second homework, I did not upload any solution for that because it's the same to the example. But I remember I have the code about it. Let me try to find it out. But I still have it. If I have it, I can probably share with you. It's in the MATLAB code. But I'm not quite sure whether I still have it in the computer.
That's okay. But it would be okay.
Yes. Do the manual, just less accurate, but it's totally fine. Okay. Any other questions? No. Good. Then I guess that'll be all today. Yeah. We have a short lecture today, and I feel like the in-person meeting would be faster. Okay, so next week we're gonna meet online, and the other week we're gonna work on the midterm exam. So if you have any questions, send me email or join the office hour. I'll always be there to answer the questions. Yeah. Good. With that, I hope you all having a good week, and I'm gonna see you next week. Maybe not. I'm gonna see you in some meetings, right? Okay. So you all have more than one classes this time, right?